if you can actually start broadcasting, that would be fantastic. All right. Good morning again, everyone, and thank you so much for joining us today. I'd like to start this webinar off by saying a warm hello to Professor Gupta.
Great. So welcome to this webinar. As you know, that there has been a lot of news media stories about shortage of ventilators and a lot of efforts about people trying to create emergency ventilators. Many conventional manufacturing organizations being reconfigured to start producing emergency ventilators, and a lot of open source effort which are coming up with design for emergency ventilators. Large number of students at USC are also interested in helping out with this cause of rapidly creating and producing emergency ventilators in enough quantities so that hospitals which need access to them can have them. So what we have been doing is basically at USC reviewing different kind of emergency ventilator designs. And this effort is led by Professor Bermejo-Moreno, and he will be our featured speaker, and he will tell you in a few minutes about different designs which are out there and what they accomplish and how those designs can be useful. A second effort that is going on at USC is that a graduate student enrolled in AME 546, or also called Design for Manufacturing and Assembly course, are also working on basically looking at these openly available design and then refining them to make them easier for manufacturing and assembly perspective and reduce cost. And those teams will be presenting basically their designs or their design refinements tomorrow at 3:30. So if you're interested in it, then you can look at it, what USC students have done tomorrow at 3:30. There are 11 different teams. They will present between 3:30 and 6:30. So with that brief introduction, I'm going to give floor to Ivan, and he will basically present our forum's summary and findings on emergency ventilators.
And as a quick interruption, if you can put all of your questions as Ivan is going through his presentation in the Q&A chat box right down below, we will make sure that we approach those questions at the end of his presentation.
All right, so thank you very much, Skye, and thank you also, Tiffany, for organizing this event and for the invitation. And thank you all for attending. I'm going to share my screen now. Hopefully you can see it in a moment and start the presentation. So first I want to acknowledge the number of individuals that you have here on the bottom left. These are all the people that have been participating in the meetings that we've had, as Skye mentioned a moment ago, in this ventilator forum. And today I'm going to present the collaborative work that we've done in identifying some of the open source ventilators that can be promising and some of the efforts that we can improve upon. I want to start by mentioning that I'm not an expert in respiratory disease or in even mechanical ventilation systems. So my expertise is actually in turbulent flow simulations applied to high-speed flight and propulsion, so very different from what I'm going to tell you about today. So please take this presentation mainly as a compilation of information, and then we're going to open a dialogue, so hopefully we can all learn from each other. This is the outline of the presentation. I'm going to start briefly by motivating this topic. Then I'm going to describe a little bit the mechanical ventilation systems and introduce some concepts that from the standpoint of fluid mechanics are important for our designs. Then I'll tell you a little bit about the minimal requirements that different medical authorities have issued some guidance about for these efforts on emergency ventilators. And then we'll have a look at some of the open source designs And finally, the activities within the aerospace and mechanical engineering department here at USC. And then we'll open the dialogue for everyone to participate. So the motivation comes clearly from the COVID-19 pandemic and the fact that it can lead in many cases to this acute respiratory distress syndrome, ARDS for short. And there is a cascade of events that happens through that process. Let's see if I can bring the laser pointer. So as you can see here, there is a rapid invasion of the lung cells. That invasion of a virus is going to affect the epithelial cells that are lining the airways. And then those airways are going to be flooded with debris and fluids, leading eventually to pneumonia, possibly, and then respiratory failure. And in those cases, the patient may require mechanical ventilation. This is a visualization of a 59-year-old patient by the George Washington Hospital, where you can see in green all the damage or infected tissue that is affecting a large proportion of the lung cells. And as you can see here on the right figure, in the ARDS condition, you have these inflamed air sacs that are going to be filled with fluid. So it's more difficult for the patient to get the oxygen to the blood and to get the CO2, the carbon dioxide, out from the bloodstream. So how prevalent is mechanical ventilation in critically ill patients? This is a study from the UK from a few days ago on about 4,000 patients. Is the largest that I could find online. And you can see that for patients that were admitted to critical care, more than 95% of them, they required some kind of ventilation. The majority of them required advanced ventilation. And here you have the outcomes. In blue, the discharged patients from the ICU, and in red, the ones that died. And as you can see, advanced ventilation is helping, but it is not helping as much as it does in patients that are not affected by COVID-19 with other pneumonia. And so the statistics are basically inverted. 35% of them will survive with advanced ventilation, whereas 65% died in this study. So this is something somewhat surprising that is the subject of ongoing debate in the community, why that happens. But even then, it's remarkable that advanced ventilation can save up to this number. In terms of the shortage that has been discussed at length over the last few weeks, where are we at the moment? This is again a study from a few days ago on a projection. These are projections from this day onward, and the need for ventilators that is projected in the period of time until August. There is a couple of caveats here that I should mention. This is assuming that the current physical distancing measures that have been taken in many places will continue until the infections are minimized and until containment is implemented. So we have to be careful about interpreting these numbers. But basically, the projection is that there is not going to be a shortage in the United States at the national level, because the number of ventilators at the moment is about 105,000. And the number of needed ventilators projected is about 30,000. Now, this doesn't answer the question of future waves, so there may be a need for emergency ventilators in the future. So all the effort that is put now can help in the future to mitigate this possible shortage. And then there is also the issue of local and global shortages in other countries, or even within the States in different places. In the States, this is addressed by the Dynamic Ventilator Reserve Program. This is a federal program that tries to move ventilators where they are needed. All right, so this is a picture that is much better in that regard than what we had projected. These models had projected several weeks ago. In terms of the types of mechanical ventilation, there is non-invasive ventilation, typically through masks or helmets. In the case of COVID-19, helmets are important because they can contain the virus from aerosolization. And then the one that I'm going to focus on today is invasive ventilation, the one that requires intubation. There are some risks associated with this invasive ventilation, and here you have some of them. Damage to the lungs, lung collapse, pneumonia that is associated with the ventilator if the circuits are not clean, and the atrophy of the diaphragm. So this requires typically a process of weaning, which is the gradual withdrawal of the ventilation support. With this in mind, it's important to notice that many of the emergency ventilators that are designed, particularly open source, some of them lack this approach to withdraw the patient from ventilation, which is important in the medical setting. And then I want to mention also that both of these non-invasive and invasive approaches to ventilation require circuit supplies. And there is urgent calls that are in effect now for non-traditional sectors of manufacturing to replenish the inventories of circuit supplies. So that's another topic for possible help out to the community, from universities and small businesses. So mechanical ventilation that I will describe today in these open source emergency ventilators is mainly based on positive pressure ventilation. This is trying to push air into the patient lungs, which is the most common nowadays, as far as I understand. And even within this type, the most common by far among the different open source designs is volume control. So you preset the air volume that you want to push into the patient lungs, and then you can monitor other variables. A bit less common in these open source emergency ventilators is the pressure control, but I'll highlight one of the examples in the 5 cases that I have selected today. And then there is the 3 modes: control, assist, and mixed. And most of them, they are oriented towards the control mode of ventilation. And this typically involves the patient being unconscious or sedated. So the patient is not actively participating in the breathing. In terms of the mechanics of ventilation, this is a typical cycle. On the top, you have the air pressure given in centimeters of water. In the bottom plot, you have the flow. So this is for a particular type of constant flow volume ventilation. So initially in the inspiratory cycle, you have a constant flow volume given, and then that's going to stop. At that point, we reach the peak inspiratory pressure. This one has to be controlled so that it does not exceed some values. Then there is going to be the inspiratory pause. The pressure decreases to the plateau pressure value, which is also an important factor to consider and monitor. And then there is the expiratory cycle, part of the cycle, where it's going to decrease to this value, which is above the atmospheric pressure. So this value is named the positive end expiratory pressure, or PEEP. And the purpose of having a positive end expiratory pressure is to keep the lungs open. So here I have some of the rationale behind this positive pressure at the end of the cycle. So it keeps the lungs open, stabilizes the alveoli, improves oxygenation, and other things. On the negative side, it's going to produce possibly overdistension and reduce the cardiac performance. So it's another important parameter to either control or monitor. So besides that, most of the open source ventilators that I'll talk about today are going to control the tidal volume. This is the air volume that is exchanged per respiratory cycle. And there are some standards here. I give you one protocol that is quite commonly used for ARDS. Then there is the respiratory rate, another setting that you should be able to control. This is the number of breaths per minute. The next parameter is the ratio between this part of the cycle, inspiratory part, and the expiratory part. Typically, it's 1 to 2, meaning that it takes twice as long in the expiratory part of the cycle as it takes to inspire. Another parameter is the fraction of inspired oxygen, the FiO2, which is about 21% for normal breathing at room conditions, but it may be increased for patients depending on the needs of oxygen. And then there is a typical output that is monitored in commercially available ventilators. Not all of these are monitored in open source solutions, but ideally you want to monitor these quantities. And then you come intervals here. These are coming from recommendations from different protocols. For example, the ARDSnet protocol and others that I'm going to briefly mention now. A number of authorities, for example, the FDA in the United States or the corresponding one in the United Kingdom, have issued guidance on how to develop these emergency ventilators. So they have produced some minimal requirements for clinically acceptable ventilators. And this is a summary of those guidance that you can observe in these different documents. Some of them change in the range, but more or less, these are the typical values that you are supposed to provide the medical community with in the emergency ventilator. So with this in mind, what are the types of ventilators that we have? As Kay mentioned in the beginning, on the left side of the spectrum, we have the emergency open source ventilators. These are the efforts that are trying to mitigate the possible shortage of ventilators. On the opposite end of the spectrum, we have the commercial solutions. And then there is many elements in between. So you have, for example, consortiums like the Ventilator Challenge UK consortium that has taken an existing model that is commercially available, and they have produced a modification that is easier to manufacture. So this is involving the aerospace and car manufacturers. Then there is existing models that have been released for open source so that other people and industries can produce them. For example, the one by Medtronic. And then there is a bridge in between fully open source and commercial solutions that I describe here as closed or licensed emergency ventilators. For example, the Vital one by NASA that came out last Friday, I believe, or last Thursday, or the Spiderwave by Boyce Technologies that is spin-off of the Event project by MIT. So these are somewhere in between. The ones that I'm going to focus on today are the fully open source ventilators that can be found online. And there is a long list. This is actually a compilation that has been posted on the internet by some group of people that keep monitoring the developments of open source ventilators. And this list goes on for about 70 to 100 projects. They classify them according to different criteria. Some of them are not fully updated because there is a long list, as I said. So I'm going to tell you about a few of them in today's presentation. But I want to point out a few caveats. Only a few have been approved for clinical trials in humans by government authorities. And that's an important requirement because without that approval, they can never be used. Only a few have published all the information that is required to build them. Some of them have partial information, as you will see today, but only a few have all the information that you need. And finally, only a few of these projects started mass production, typically involving car manufacturers or local industry. And finally, there is a corollary to this last comment. Some of these projects that started mass production have already stopped because there is a lack of demand coming from hospitals, according to these projections that I mentioned in the beginning. It doesn't mean that they may not be used in the future, but at the moment, some of them have stopped the mass production. All right, so the one set of projects that I wanted to tell you about is this set, 5 projects. The majority of them, if you go back to the list that I showed you before, you will see that the majority of them are based on volume control ventilation, and they, in some way or another, actuate an ambu bag, which you have represented here on the right. This is a bag that is used for manual resuscitation. And the idea of these open source ventilators is to mechanically actuate this bag in place of the manual actuation that is commonly found in emergency situations. And then there is a couple of other projects that I wanted to mention briefly. The open source ventilator project by the University of Florida. This is based on a pressurized gas line. And finally, the Acute ventilator project that is based on turbine design. So this gives you a bit more control, and it's also based on pressure rather than volume control ventilation. All of these models can set the respiratory rate, the inspiratory to expiratory ratio, and also if you have oxygen available in a tank or in a pressurized line, you can set the fraction of inspired oxygen as well. So I have one slide on each one of these projects, and I have more material for some of them in case you have questions at the end, but I wanted to give you a brief overview of these different efforts. The first one is the oxygen project by Protofy. This has already passed the clinical tests, so that's why I put it first here. It has several certifications already passed, like electromagnetic compatibility, safety certification. It's meant for a durability of 3,000 hours. It's approved for clinical trials in 2 hospitals in Spain, and it's already mass produced by one car manufacturer, SEAT, also in Spain. The target was to produce 300 units a day, but last week, actually, they stopped production because of lack of demand, as I mentioned before. The nice thing about this model, despite its simplicity, is that it's fully reproducible. So they have extensive online documentation for all the legal documents, technical documents, medical, clinical trials, and so on. The materials are quite simple, so something that you can find basically in any location, pretty much. The bill of materials consists of about 100 parts. So all these projects try to simplify the process of manufacturing compared to the commercially available solutions. So 100 parts is the ballpark that you can get usually from these open source designs. Probably the most critical part is the windshield motor. So they have reconverted a windshield motor inside this box to actuate the ambo bag that you have here in the video. And then a couple of drawbacks of this design is the lack of comprehensive monitoring and alarm system. And then the replacement of the cam here that you have on the right. The cam is going to change the volume that you can push to the patient's lungs. So if you want to change that setting for the different patient conditions, you have to manually change the cam inside this box. And that is less beneficial. So ideally, you want to have an automatic way of changing the settings without having to do any manual intervention. The next project is the ambo vent. This is a similar spirit to the previous one. So it uses the ambo bag that is going to be mechanically actuated by a motor and this device here. This is produced or actually developed by the Israeli Air Force in cooperation with certain industries in Israel. And it is not yet approved for clinical use. It follows the standard that I was mentioning before, or the guidance that I was mentioning before from the United Kingdom. And it's undergoing extensive testing by the medical authority in Israel. Again, the materials are relatively simple and easy to obtain. The production is not yet detailed as opposed to the previous model, but they indicate possible approaches to manufacture it. The number of parts is similar, about 100 parts. They mentioned that the expected cost when mass produced is going to be below $1,000. So that's usually the ballpark that we are looking at for these open source designs. And then in contrast to the previous one, it has some enhanced control and monitoring capabilities. The previous one didn't have any alarms or monitoring. This one has the different settings actually that you can see here. And then the documentation is extensive, but not complete. So I don't think it's possible to replicate the model currently with the information that is given in the websites. The next case is actually probably one of the most popular in the United States. This is the EVENT project by MIT. And this has already completed clinical studies in animals. And it's fully open source, but you have to register through the website. 2 days ago, they released the prototype software. So you can check it on GitHub and use it. It is moderately documented. I believe they focus a bit more on research from what I have read in their documentation. The production is not yet fully detailed, but they include much more control and monitoring than, for example, the first project. And this project has inspired others. For example, the spider web that you have here on the right. This is now mass produced in New York by this voice technology, and it is inspired by the event MIT ventilator. So it is a quite promising design. It actually started several years ago as a student project at MIT, and now they have continued that through the COVID-19 pandemic. There is another university project among the many that you can find in the United States. This one is called the Open Source Ventilator Project by the University of Florida. And it's a bit different from the previous three. It doesn't look at mechanically actuating an ambu bag. It's going to look at taking a pressurized line, the one that you can have in hospitals, for example, with a blend of oxygen and air, and then it's going to distribute that flow to the patient. I believe they focus a bit more on the electronics and the control system, from what I have read online, a bit less so on the mechanical part, because it's not as complex as the others. And on the mechanical side, they have instructions on how to build it, but it has the feeling of more of a do-it-yourself approach compared to the other that are fully adapted to production chains. Then the cost of parts is stated as 300, again, because it has less complexity on the mechanical side, but the clinical studies are not yet detailed. I think this one is spawning also a number of efforts and collaboration across the globe. And then the final project is a bit different from all the others. This is called the Acute 19. It's not from the University of Florida. I apologize for the mistake here. It's actually coming from Spain. I should have changed the title. But it's based on a bi-level turbine ventilator system. So instead of volume control ventilation, it's going to provide pressure control ventilation. The setting is actually the inspiratory positive airway pressure. And then you can also control these other parameters that we mentioned before in the mechanical ventilation terminology. One of the advantages of this system is that it allows this weaning process that gradually removes the support, ventilation support from the patient as the patient recovers. And it also supports a different type of non-invasive ventilation, the continuous positive airways pressure. They have completed clinical studies in animals, but now they are currently seeking emergency use approval from medical authorities in Spain. It is open source, but until they get the approval, I contacted them and they are waiting until they get the approval to release all the documentation. So it is unclear when they will release the documentation. And then there is ongoing certification efforts as well, but those are a bit easier than the medical approval. All right, so this is the last one that I wanted to show. And in the last couple of minutes, I wanted to tell you about these activities within the Aerospace and Mechanical Engineering department at USC. It is clear that many students here at USC are interested in joining these efforts to mitigate the COVID-19 challenges. And as SK mentioned in the beginning, in his class for the design of manufacturing and assembly, there are a number of student teams that are working on different projects. This is a picture that SK sent a few days ago from his class. And they are improving the designs mainly from the standpoint of manufacturing cost. So these are end of semester projects, and there is going to be a presentation tomorrow. And then we are trying to launch this initiative on directed research for master students within the AME department for the summer. So this is meant for short-term design improvements through collaborative research approaches. So far, we have had a massive student response. Here is the number of responses that we get from students in the master's program to work on 8 activities that we proposed. And this can be enhanced or augmented as the different interests of the students may come about. But you can see quite a large interest in mechanical design, followed by sensing, monitoring, and control, automation of manufacturing, then the circuit supplies that I mentioned that are common to both invasive and non-invasive ventilators, and then several other activities. So with this overview, I wanted to conclude the presentation and open the floor for a dialogue or a discussion and questions as well. So thank you for your attention.
Thank you so much, Ivan. So we did have a hand raised from the audience, Mr. Hassan, and I'm so sorry for butchering your last name, Karamandan. I'm going to allow you to unmute right now. All right, Hassan, are you there?
Yeah, I'm here. What I'd like to ask, the new that USC has, is that coming up? Is that going to be under production?
I imagine to refer to the efforts that are launched at the moment in the AME 546 class. If that's the question, then I don't think these are going to be meant for production. The approach that we are taking at USC is more on the educational side. So we are not trying to develop a quick prototype that we can put in production at the moment, based primarily on this motivation that I mentioned initially, that there is currently no shortage in the United States of ventilators. So we want to take this opportunity to put more emphasis on the educational aspect of the endeavor. So some of the students in the department may have lost their internship opportunities in industry that they had lined up for the summer. So the approach now is to try and provide opportunities for learning enhancement within the department. And hopefully, if these designs are fruitful, we can start prototyping some of them, maybe in the Center for Advanced Manufacturing that Skay Gupta leads and directs, or maybe in other facilities within the AME department. But at the moment, there is not a race within the USC context to produce a prototype in a very short time.
So I have a following question, sorry. This following question, do you see that in short period of time, near future, we would have portable ventilators, so it would be easy to take it from one patient to another patient?
So let me answer the question from a slightly different perspective. So what is going to happen is that, after tomorrow, when we have evaluated basically different designs and students have figured it out, what the cost might be. And as we start transitioning into summer, and as the students start talking to different people and better understanding what the real needs are, then our responses are going to be a little bit different what they are today, right? So if it turns out that as students in the summer start working on it, of course, we will have a lot of good starting points from the work which has been done by AME 546 students. And if it turns out that portable ventilator is the, a real need, and there's a real need to do that, then we'll be certainly happy to evaluate it. It's just that right now, if we think about what limited knowledge that we have, so far our focus has not been on that. But on the other hand, we will the students who will start working on it for research during summer will talk to relevant, potential stakeholders, and then they will refine the concept around it. So there's a chance that we might end up doing it if there's a compelling need for that.
Thank you.
Thank you so much. And we had another question actually emailed in a couple days ago. Yvonne SK, why do you think the survival rate for COVID-19 patients on ventilators is so low, 30% versus 65% of non-COVID-19 patients? And how can the new ventilators be designed to improve this survival rate?
So I will plead complete ignorance on the medical end of spectrum. We can take that question with our collaborator at Keck and then get back perspective on it, but I am not in a position to answer that question.
Yeah, again, more or less in the same situation. The only thing that I can add is what I read about, but this is not a medical expert opinion. This is just based on information that you can find online. And there is a number of articles, for example, here on the screen. Hopefully you can see one of them on Science, published last Friday, I believe. And they talk about the differences between COVID-19 ARDS and other types of ARDS situations coming from pneumonia. And what they describe is how COVID-19 affects not only the lungs, but also other organs in the body. Also, I noticed in the guidelines that they provide from the UK on the rapidly manufactured ventilator systems, they give a little bit of emphasis to those differences. So for example, here I have highlighted the respiratory secretions that are much more copious than in normal critical care pneumonia. So that's going to probably affect the way that you design a ventilator that is more meaningful for COVID-19 patients. Also, they observe, at least in the UK, this may be localized, but at least in the UK, they observed that the duration of intubation is longer than normal. And they propose that ventilators that are suitable for this COVID-19 pandemic, they should be capable of supporting spontaneous breathing modes. So there is other references that you can check. For example, this why ventilators may not be working as well for COVID-19 patients as Dr. hoped. Again, this is information that I found online, but I cannot give you a medical perspective on it. Only some thoughts about what I read.
Fantastic. Thank you so much for that. And then we also have a question that came in during your presentation about the references used in preparing the projections on your motivation foil.
All right, so let's go back to those slides. Yeah, so I tried to put all the references here in case you want to check them out. So there are 3 slides on the motivation. This reference comes from the George Washington University Hospital. This was actually released a few weeks ago, probably to give some sense to the community of how much it affects the lungs, the patient's lungs, as opposed to maybe other ARDS conditions. This comes from, I believe, USA Today. It's a nice representation of what happens in the exchange of oxygen and CO2. So I chose this because I didn't have time to prepare something myself. So hopefully it's okay to use those. And then in terms of the statistics, this one is coming from this program. So this is the Intensive Care National Audit and Research Center. And you can find many more statistics actually from those reports. They update them basically every week. And this was downloaded on April 24th during the weekend when I was preparing most of the presentation. The next one is coming from COVID-19 health data. And this was updated yesterday. So I took the data from yesterday. You can check by country. Within the US, you can check by state. They not only have information about the ventilation requirements, but also the number of beds that are needed in the critical care units, or many other statistics, the number of cases reported. So you can check by country, you can check by region within each country, and so on. And yeah, I think regarding the motivation, those are the sources that I could point out. This is, as I said, the largest cohort of patients that I found, but there may be others that I didn't find. Hopefully that answers your question.
Yeah, Ivan, so the question was, I think there's another question by the same person, and that is about basically the projection data.
Oh, the projection. So this projection is, again, updated pretty much every few days. And what you have here is the average projection in the dashed line, and then the uncertainty with a 95% confidence interval. So as we collect more, as they collect more data, they can get better predictions. But again, I want to emphasize the caveats here. So this is assuming some behavioral particulars for the society. So in particular, it's assuming physical distancing is still in place. So it is still a question mark how this is going to evolve now that many regions are changing these directives in different states. So this could change in a few days, or it could continue this way. I don't know if that's properly addressing the question. Let's see if I can read it on the chat.
All right, and while we're bringing up more additional chat questions, we actually have another question coming in from Taufik Razak. I'm going to allow you to speak right now.
Hello, Dr. Ivan.
We can hear you.
Yeah, my question is there any chances for any computational visualization and computational research in the area of ventilator design that would be useful?
That's a great point. Yeah. So we didn't talk much about the fluid mechanics that go into the design of ventilators, because maybe that has been so far a secondary focus, but that's something that several students have pointed out here. On top of this list of 8 activities that we proposed, there is interest in fluid mechanics, so computational fluid mechanics of these designs, as well as data analysis. So there is definitely a lot of possibilities that open up in improving these ventilation systems, also in adding possibly medication or other approaches for ventilation combined with more benefits to the patient. So definitely there is many studies that could be done on the CFD side, computational fluid dynamics side.
Yeah. Dr. Ivan.
Thank you.
All right, do we have any other questions from the audience? I believe we already answered all the questions in the Q&A box. Okay, we'll give everyone a few seconds just in case we have anything last minute coming in. Okay, fantastic. Yvonne and SK, do you have anything to add before we conclude the presentation?
So basically, just again, information about tomorrow when USC students will present basically designs, and there'll be 11 different presentations, 15 minutes per team, and that's going to go on between 3:30 and 6:30 tomorrow. And that's the one where people who are interested in signing up for it, who should they reach out to? Should they send an email, or how does that work?
Yes, so after this presentation, I'll send the recording of today's webinar as well as the event registration link for tomorrow's class showcase to everyone in case they want to join. We do have 20 spots still available, so there's still time to sign up for that. All right, fantastic. Well, thank you all so much for joining us today, and special thanks to Yvonne for putting together such a wonderful presentation. And thank you as always, SK, you're one of our favorites. Thank you so much for participating in this, and we will send out this recording to everyone participating today, and it will be posted online.
Okay, again, so one more thing, Tiffany. So again, we should thank Tiffany, Jane, Christy, Mata, all the wonderful people who make this happen. Without your help, clearly, you will not be able to do so. So we really, really appreciate all the hard work that you do. So again, to acknowledge that, basically making presentation is hard work and everybody knows that. But, technologically making an event successful is an equal amount of hard work. And often that gets ignored. So I just want to make sure that we all acknowledge that, how hard you work and how appreciative we are. And this is allowing us to basically move forward and share information with the community. So once again, thank you, all of you.
Thank you all so much. And fight on. Thank you, SK.
I want to say also thank you very much to all of you, Tiffany and the whole team, because you've made it so seamless and smooth to get things out and broadcast. So thank you very much.
We really appreciate it. Thank you so much.
Okay, thank you.
All right, have a great day, everyone.